Course 3, Lesson 61, we are looking at sequences. And two different types of sequences. We have arithmetic sequences, which has a constant difference between the terms, and a geometric sequence, which has a constant ratio between the terms. So what I mean by constant difference is, let's say that we have this sequence, an ordered list of numbers that has a pattern, 3, 6, 9, 12. And we would say, well, each one of these we add 3 to the previous term to get the next term. So the first 4 terms are given. We need to come up with a rule in order to find additional terms. Now, something that we use with these sequences is the position of the term. So we call the position of the term n and the actual term value a sub n. What this does is say, if we have term 1, a sub, not n anymore, a sub 1 is 3. And as 2, a sub 2 is 6. A sub 3 is 9. A sub 4 is 12. The question is there a pattern between the term number and the actual value of the term a sub n that we could figure out a formula for? Because unfortunately, if we do something like a sub n is equal to n plus 3, like we kind of want to, once we start plugging in n values, a sub 1, we would see that 1 plus 3 doesn't equal our first term value. So that's not going to work. But maybe we look between the term number and the actual value. So 1 to 3, 2 to 6, 3 to 9, 4 to 12, and we see that, well, each time I'm actually multiplying the term number n by 3. We're multiplying it by 3, and that gives me my value. Because when I plug them in, I would say a sub 1, so a first term, is 3 times 1, the term value. And that gives me 3. That works. A sub 2 is 3 times 2, so we get 6. That works. A sub 3 works and gives me 9. And a sub 4 also gives me the correct value. So this rule of a sub n is equal to 3n does give me the correct value, which means I could continue this pattern and find a sub 5. That gives me 3 times 5, that's 15. A sub 6 gives me 18. A sub 7 gives me 21. What's really nice about this way of finding the formula is that I could go into really crazy numbers. You know, let's say we want the 54th term, a sub 54. All I need to do is do 54 times 3, and that will give me my answer. So let's see, that's 162. I don't even have to go up to in the 50s at all. I can skip right to our 54th term in the sequence and find my answer. So it had a constant difference of 3 between each term. That makes it arithmetic. We could also have geometric sequences. So geometric sequences have a constant ratio like this one, 1, 3, 9, 27. So the constant ratio, what we're saying is if I do 3 divided by 1 and 9 divided by 3, 27 divided by 3, 9 divided by 3, 27 divided by 9, I'm taking the second term divided by the first, third term by the second, fourth by the third, fifth by the fourth. Okay, that constant ratio is 3. So what are the next 3 numbers? Well, I would be doing 27 times 3 is 81. We get the next 243, and then let's see, that times 3, 243 times 3 gives me 729. Those would be the next terms in the sequence. Now, what we did previously, the constant difference, so we added 3 every single time. In our equation, it actually worked out that we multiply, which kind of makes sense because repeated addition, like we do here, repeated addition, that can be shown as multiplication. So if we have repeated multiplication, we take each of these and multiply by 3 every time. That means if we have repeated multiplication, exponents must be part of our answer. And they actually are. This one ends up, and we'll look at the formal equation in just a minute. This one ends up saying a sub n is equal to the ratio to the n minus 1 power. We'll look at how we get that in just a moment, but just know when we have this repeated multiplication, we actually use exponents to show the formula. All right, so with this arithmetic sequence, we have a specific formula that we use. You can actually graph this, okay? Arithmetic sequences are going to be linear, okay? So if we take this, here, I'll show you. If we take our number and the value, okay, number of the term goes on the x-axis because it kind of acts like x, and the value of the term goes on the y-axis. So we have our values. I'm going to go up by 3 with my values. We see that for each one, I'm going to have a straight line. And that happens with my arithmetic sequences. I have a straight line for my arithmetic sequence. It is linear. You can think about, we found an equation of a sub n is equal to 3n. Well, that's like saying a sub n is actually y, and x is n. So we have y equals 3x. That would be the equation of this line. It has a slope of 3 and a y-intercept of 0. Whereas when we look at our geometric sequences, they do not look like straight lines. Okay, so if I were to put this on a graph, I'm going to do my best here to put a good representation. We'll go up to 27. So I can say, all right, my 1 goes to 1. It has a dot about there. 2 goes to 3. 3 goes to 9. You can already start seeing that this is not linear. 4 goes to 27. And then 5 would go all the way up here to 81. This is actually a curve that goes through our geometric sequence. Okay. This is actually exponential growth, by the way. So we want to write a formula. Well, we figured out that we get a sub n equals 3n. The general formula that we actually end up using for this is this one right here. A sub n is equal to a sub 1 plus the difference times n minus 1. So for this formula, for the sequence that we had earlier, we'll see that if we do a sub n, that's going to equal my first term, 3, plus the difference, which in this case we added 3 each time, so we have a difference of 3 times n minus 1. And when we expand it out, we get 3 plus 3n minus 3. And so when we combine, we do see we get a sub n is equal to 3n. This arithmetic sequence will work for any arithmetic sequence. This general formula will get you very far. So let's say we have a sequence like 23, 28, 33, 38, 43, and so on. Well, we see we need 2 different pieces. We need the first term, a sub 1, and we need the difference. So a sub 1 in this case is 23. And the difference, we're adding 5 each time. So we can plug it into our formula to say a sub n is equal to 23 plus the difference of 5 times n minus 1. So we expand to get a sub n is equal to 23 plus 5n minus 5. We just combine like terms to find that. The formula for this sequence is 5n plus 18. What this allows me to do is I could find the 100th term, millionth term, without having to count up all the way. All right? So, memorize the general formula or realize that this is very, very similar to a linear equation. Basically what we're doing is when we get down to it, this formula, if we replace a sub n with y, it's y equals m slope x plus b. We're basically finding slope and y-intercept by plugging into this formula because arithmetic sequences are lines. Okay, and then geometric sequences. So I told you that we have a general formula for this. And like I told you earlier, the formula for this is 3 to the n minus 1. This works because if we plug in the term value, a sub 1, we get 3 to the 1 minus 1, which is 3 to the 0, so it's just 1, and that's exactly what I get for my first term. A sub 2, second term should be 3, and we do get 3 to the 2 minus 1, so 3 to the first is 3. Third term, we should get 9, and we do. 3 to the 3 minus 1, so 3 squared is equal to 9. What this means is that I could find the 100th millionth term just by doing, maybe we say we want the 50th term, a sub 50. That would equal 3 to the 50 minus 1. So I would just have to do 3 to the 49th power to find my 50th term in this sequence. The general formula, very similar to the arithmetic, we have a sub n is equal to our first term, a sub 1, times our constant ratio, not constant difference, constant ratio to the exponent of n minus 1. So that let's say we had a geometric sequence like 3, 6, 12, 24, 48, and so on. Well, we can see that our constant ratio is 2. I multiply by 2 for each one of these. And our first term, a sub 1, is 3. So we could plug this in and say my general formula, a sub n, is equal to 3 times 2 to the n minus 1 power. We actually have to leave it there because exponents come before multiplication in order of operations, so we could not put that as 6 to the n minus 1. That is not the same thing. But we could find something like a sub 10 and say a sub 10 would be 3 times 2 to the 10 minus 1. Or a sub 10 is 3 times 2 to the 9th power. And we could multiply that out and find my 10th term. All right, let's just describe these as arithmetic, geometric, or neither. So 1, 2, 4, 8, 16. Let's see. Let's see if it's arithmetic. So we add 1, add what? Nope, that's not going to work. Maybe times 2. Okay, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Yes, this is geometric because we multiply by the same thing. 2, 4, 6, 8, 10. Well, we're just adding 2 each time. That's arithmetic. 1, 4, 9, 16, 25. Well, it looks like they're all squared, but do we have a constant difference? We have a constant difference of 3, 5, 7. No, that's not constant. Maybe multiplication 1 times 4 is 4. 4 times 4 is not 16, not 9. So this is neither. This is neither. Okay, find the constant difference. 1 to 5, 5 to 9, 9 to 13. Well, that's constant difference of 4. What's constant ratio? Well, we could see pretty quickly that it's multiplied by 5, or if you can't see that quite yet, do 25 divided by 5, 125 divided by 25, 625 divided by 125. That gives me 5. Okay? And right, the first 4 terms of the sequence described by each formula. So I need to do a sub 1, which gives me 2 times 1, so that's 2. A sub 2 is 2 times 2, which is 4. A sub 3 is 2 times 3, which is 6. And lastly, a sub 4 is 2 times 4, so 8. So my first 4 terms of the sequence is 2, 4, 6, 8. For the second one, a sub 1 is going to be 2 to the 1 minus 1, which is 2 to the 0, so that's just 1. A sub 2 is 2 to the 2 minus 1, which is 2 to the first, so that is 2. A sub 3 is 2 to the 3 minus 1, so 2 squared, which is 4. And lastly, a sub 4 is 2 to the 4 minus 1, so 2 cubed, which is 8. meaning that this geometric sequence starts out with 1, 2, 4, 8. All right, so that's our arithmetic and geometric different sequences. I hope this was helpful for your homework and for studying.